And we're back and better than ever in 11.3, Reactions in Aqueous Solution. In this section we're going to take a look at the various equations that you can use to describe reactions that take place in water. We will also be showing you what are called solubility rules, which you can use to predict whether or not a precipitate will form, whether or not something is soluble or not. And then we'll wrap up the section by giving you reactants and then asking you to predict the products and also predict whether or not either one of those products will be a precipitate. Alright, so let's start off by taking a look at the equations. The first one is a molecular equation, and that's an equation that you're actually familiar with. For example, if we take silver nitrate solution, so we're going to write AQ behind it for aqueous, plus sodium chloride, AQ, it's a solution. This is going to be a double replacement reaction where the silver will replace the sodium will replace the silver, and you'll be left with silver chloride, which is actually going to be a solid. You'll learn why later on in the section, and sodium nitrate, AQ. So that's a typical equation that you've been working with periodically throughout this trimester. It shows everything, shows all the compounds as molecules. Now that might not necessarily be a good indication of the reality of these molecules. For example, if you take a look at silver nitrate, and I'm going to draw this above it, in the solution there's no AgNO3 floating around. What you actually have are individual silver ions, they're plus 1, and individual nitrate ions, those are minus 1s. So we'll put just a couple of each in those. And they're floating around on their own. Similarly, the sodium chloride, we'll go ahead and draw that in right here. If you have a container of that, you do not have any NaCl's floating around. You have sodium ions and you have chloride ions floating around, but no NaCl individually bonded together. And so that actually is a better representation as to what the reality of the silver nitrate and the sodium chloride are in solution. Now when you mix those two together, so we'll put these into one big container now. The silver chloride is going to be a solid, and it's going to be piled up on the bottom right there. It's a solid, and it is going to sink to the bottom. Now on the other hand, the sodium nitrate is AQ, dissolved in water, so you're going to have individual nitrate ions floating around, and you're going to have individual sodium ions floating around. You won't necessarily have any NaNO3s. And so if you want to write an equation that better indicates what the molecules look like, or what the ions look like, you might want to choose a complete ionic equation. Let's go ahead and scroll down just a little bit. In a complete ionic equation, instead of writing AgNO3, you're going to write it as silver ions, dissolved in water, and nitrate ions, dissolved in water, AQ. Because that's really how they exist in that beaker. When you add that to the sodium chloride solution, you actually have sodium ions and chloride ions. You do not have sodium chloride. Now when you form your products, you are not going to write the silver and chloride separate, because in the beaker they are not. They are actually in a pile in the bottom, bonded together. So you're going to write that as AgCl solid. However, the sodium and the nitrate ions are in fact floating around as individual ions. Lots of them. So this complete ionic equation does a better job of indicating the reality of their existence in the beakers. If they're ions, we list them as ions. If they're a solid stuck together, we list them as a solid stuck together. Now if you notice, before the reaction, the nitrate ions are floating around in this particular beaker right here before, and they're still floating around in the beaker, or in a beaker, afterwards. Similarly, the sodium ions are floating around on their own before and after. And if you notice in the balanced equation, the overall equation, both the sodium and the nitrate ions are as individuals before and after the reaction. In fact, they did not do anything going from reactants to products. So we call those spectator ions. Similar to fans in the stands of a football game or a basketball game, we call them spectators. They simply watch the game and do not participate in the game. Spectator ions simply watch the reaction but do not participate in the reaction. And so they're the same before and the same after, and since they do not actually participate in the reaction, we can eliminate those from the equation. They don't actually do anything. So what you're left with is silver ions in solution and chloride ions in solution, forming silver chloride, solid. That is actually the only thing that happens when you mix those two solutions. We call that the net ionic equation. The term net simply means overall. It's similar to getting a net paycheck from your job. When you look at your paycheck, there's going to be a gross pay, which is what they would give you if they took your hours times your hourly wage, but then they have to take out all the taxes. And what you're left with is your net salary or your net earnings. It's the same thing here. Once you remove all of your spectator ions, you're left with your overall net ionic equation. Alright? Now, this doesn't just pertain to double replacement precipitation reactions, although that is what we're going to be focusing on the rest of the way. It also pertains to any type of a reaction. For example, let's use a single replacement reaction where you take lead replacing silver. When the lead replaces the silver will turn back into its elemental state. The lead will become an ion and go with a nitrate ion. And so there's the equation. To balance it, you would need to put a 2 out front of the silver nitrate and a 2 out front of the silver. Now, again, that does not necessarily reflect accurately what's going on in the solutions. Yes, you do have lead as a solid, but the silver nitrate, just like in the last reaction, will be floating around as individual ions. The silver is a solid. The lead has become an ion, a 2+ cation, and the nitrate is still an anion floating around in the solution on its own. So the nitrate ion is the same before and after the reaction. The lead went from its elemental state to an ion. The silver went from an ion to its elemental state. So those two actually underwent a change, but the nitrate did not. That would be the spectator ion. And so we can remove that spectator ion from the net ionic equation. So overall what happens is you have lead reacting with silver ions to form silver, that should be Ag, plus lead ions. And that's actually what's happening in that solution. Now, technically, you do have to balance this not only for mass, but for charge. And so if you notice, there's a +1 on the reactant side, there's a +2 total on the product side. So to balance the charge, we need to put a 2 out in front of the silver ions. So now there's a 2+ on both sides. And then we'll also have to put a 2 in front of the silver on the product side to balance for the mass. So that's actually the balancing that you need to do in this particular reaction. However, we will not be focusing on these single replacement reactions as far as the net ionic. You will have to know them. What we're going to be focusing on are the double replacement precipitation reactions. And in the next podcast, we're going to talk about the solubility rules you can use to predict whether or not a solid is going to form. We'll see you next time.